This is John Whitaker for the Mathematical Analysis class. This is our 28th video lecture, and this is a makeup lecture. And I'm not sure this is the way that we should be handling it, but it is what I'm going to do. We're going to have this lecture with nobody here in the room, and that I'm trying to make up for a day or 2 days, actually, that I missed because of not being here with my wife having been put in the hospital for a few days. She's out now, and I want to thank everybody for their well wishes, and I think it very much helped for everybody's positive attitude towards her getting better, and she's getting better. And so I'm not so sure this is the best way of handling it without people being here in the room, but I got enough confidence in you guys to understand the material, and in me in presenting the material for us to understand what's going to be covered today. And today is a big day. Lots of important things we're going to be talking about. We're going to conclude the proof of the sequential criterion for function limits. That's what we're going to start with today. Let's go ahead and get started. So here's what it says. The theorem is the sequential criterion for function limits. What it says is, it says, if we let A be a subset of R, F go from A to R, and C be a cluster point. Okay. Then the following statements are equivalent. So this is really the preface of an if and only if statement. And here's what it says. It says the following. It says, 1, the limit as x goes to c of f of x equals to some number L. And 2, if you take a sequence, or if you take any sequence that's a subset of A, that's the domain of F, with none of the terms of the sequence being C, and the limit as n goes to infinity of x of n equal to C, then that's going to force the sequence f of x of n. I say that's a sequence again, f of x of n. Converges to L. So this statement relates limits of functions to sequences, and we have learned a lot about sequences, so that's wonderful to be able to relate limits of functions to sequences, something we've learned about. Let's look at the proof. So it's like an if and only if statement, so we're going to prove 1 implies 2 and 2 implies 1. So here, and we had started this before, to show some proof, we're going to have our setup. We're going to have A as a subset of R. That's the domain of our function. F goes from A to R. And C is a cluster point. Okay. So here, to show 1 implies 2, okay, we're going to let f of x, the limit as x goes to c of f of x be equal to some number L. Okay. We want to show, and I'll write this down, I'll say this, we want to show part 2, that is, if you give me any sequence that's in A, none of its terms are C, but that sequence converges to C, then f of that sequence, that's f of x of n, converges to L. Okay. So to show that that's true for all sequences that fit the criterion of the second part of the statement, we just take a generic one that does. So we're going to let x of n be a sequence in A with x sub n, first of all, being different from C, and that's true for all n known natural numbers, and the limit as n goes to infinity of x sub n equal to C. What we're going to do, we want to show, we will show, the limit as n goes to infinity of f of x sub n equals to L. That's what we're going to do. All right, this is a limit of a sequence, and the way that we can prove the limit of a sequence is this particular L. Is we use the definition. We're going to let epsilon be greater than 0 be given. We need, well, for a sequence, we need a k on the natural numbers, such that for all n bigger than or equal to k, the absolute value of f of x sub n minus L will be less than epsilon. That's what we want to show. We've got to find that k. Okay. So here, let us begin with what we know, and that is what we're assuming is that since the limit as x goes to C of f of x equals to L, and we've been given an epsilon, that means there exists a delta greater than 0, such that for all x element of A with 0 less than x minus C is less than delta, I'm just using the definition of the limit as x goes to C of f of x equals to L. Then the distance between f of x and L will be less than epsilon. Hey, I know all the f of x, all the output values are really close to L within epsilon units, as long as the input values are really close to C. What I'm trying to show is that f of x sub n is really close to L for an x sub n, a sequence x sub n that converges to C. Well, if the sequence x sub n converges to C, that means that the distance between terms of the x sub n and C are also very small. And what this is, if they're within delta units, the output value is going to be within epsilon units of L. And so that's going to be able to give us the conclusion of this part. So here's the way we formally write it up. We'll say since x sub n is a subset of A, a sequence in A, so it's guys in A, with x sub n being different than C for all n element of A, and the limit as n goes to infinity of x sub n equals to C. So it's this part that I'm going to tackle first. Then there exists a k. Hey, that's what's going to give me a k that I'm looking for. It's the fact that the x sub n converges to C. It's the element of natural numbers such that for all n bigger than or equal to k, the absolute value of x sub n minus C will be less than, well, be less than anything I want. Of course, I need to see what that is to pick the k that I need. But the thing that I want it to be less than is delta. Because if you're within delta units of C, the output values are within epsilon units of L. This limit as n goes to infinity of x sub n equals, it really gives me this part, okay? So, since I'll just say it this way. I'll verbally say it, I won't write it. So look, x sub n's are never C. So that means we have, for all n bigger than or equal to k, 0 less than x of n minus c is less than delta. So since the sequence x of n is a subset of A, and 0 is less than x of n, and for all greater than or equal to k, 0 is less than x of n minus c is less than delta, then by the fact that the limit is x goes to c of f of x equal to L, we're in this situation, so the output values, and the output values of f of x of n minus L will be less than epsilon. So here's what we get. So for all n greater than or equal to k, f of x of n minus L is less than epsilon. And that's what tells me that the sequence of x of n's converge to L. I'll write that down, and that will end this direction of the proof. Okay, so that's what we got. So now we want to show that the sequence part of the theorem implies that the limit of the function is L. That is, that 2 implies 1. We will prove the contrapositive. And that's what our book does too. That is, we will show that if the limit as x goes to c of f of x is not L, then there exists a sequence x of n in A with x of n being different than c for all n element of the natural numbers, and the limit as n goes to c, n goes to infinity, I should say, x of n equals to c, but the limit as n goes to infinity of f of x of n does not equal to L. So that's what we're going to do. So again, what we're doing is we suppose let the limit as x goes to c of f of x be different than L. May not exist, okay? But we're saying it's not L. So we've got to create this sequence. Okay? So how do I create this sequence? Well, I do it based on the fact that limit as x goes to c of f of x equals to L. So what is it is different from L? Not even. What does it mean for the limit as x goes to c of f of x is not L? It means that the definition of what it means for the limit as x goes to c of f of x to equal L isn't wholly true. It isn't true, it is not true, that for every epsilon greater than 0 there exists a delta, such that if you look at numbers in the domain of the function, x element of A, such that x is different than c, but really close to c within delta units, then the output values are within epsilon units, f of x minus L. And then epsilon units of L, the output values are within epsilon units of L. That's not true. So what that means is that it's not true for every epsilon this happens. So that means there exists an epsilon naught greater than 0, such that no matter what delta you pick, so it's for all delta greater than 0, there exists a number, an x, I'm going to call it x of delta. Okay? X of delta, element of A, with x with 0 less than x of delta minus c, so it's really close, the x of delta is really close to c, but f of x sub delta minus L will be bigger than or equal to epsilon naught. That's what the limit as x goes to c of f of x being different than L gives us. So what we're going to do is for each n, we're going to let delta, we're going to look at this kind of a family of deltas. So we're going to consider delta to be equal to 1 over n. That's for each natural number. Then there exists, I'm going to call it x of n, element of natural numbers such that 0 is less than x of n minus c, which is less than 1 over n, but the absolute value of f of x of n minus L will be greater than or equal to epsilon naught. And that's true for every natural number n. Get this x of n. So here, look, what I'm thinking is this. When you take delta equal to 1, because the limit as x goes to c of f of x in now, that means there's this epsilon naught. And that epsilon naught is fixed, okay? And such that when n is equal to 1, we take delta equal to 1, but there's an x of 1 that's in the domain of A. Oh, I didn't write that. So it's that x of n is element of A. And x of n is within 1 unit of c, but f of x of 1 minus L inside f sub A is greater than or equal to epsilon naught. And that's true for when n is equal to 1. But then we do it for when n is equal to 2. We get another x of n. That's in A, it satisfies this, 1/2. But f of x of n minus L, f of x of 2 minus L is greater than or equal to epsilon naught. And so we keep doing this. So we have formed the sequence. X of n. And what do I know? I know each one of the x of n's are in A. So the sequence, the set of all these guys, is something that's a subset of that. All the terms are in A. And now I know that 0 is less than x of n minus c. So that means for each x of n, they can't be c. Because if they were c minus c inside absolute values would be 0. But we're having the requirement that whatever the absolute value of x of n minus c is, it has to be greater than 0. So x of n can't be c. So I'll write that down. X of n is different from c for all n on the natural numbers. And since x of n minus c inside absolute values is less than 1 over n, that part right there, that forces the limit as n goes to infinity of x of n to be equal to c. And that's based on a theorem we did not that long ago. Or we did it a good while ago, having to do with sequences. It was this theorem 3.110, I think. But I mentioned it not that long ago. And so we're using it again. So since x of n minus c is less than 1 over n, then the limit as n goes to infinity of x of n equals to c. But here, the fact that f of x of n minus L is always greater than or equal to this epsilon naught, that tells us that the limit as n goes to infinity of f of x of n is not L. And so that's how we form the sequence, and we prove by the contrapositive the second part of the sequential criterion for function limits. Well, based on that, we get this divergence criteria for functional limits. And I'm not sure that I had said this before. If I have or haven't, I'm saying it now. So I'm going to write up a definition. About divergence. But first, let's recall we've been using it. So recall, we have the definition for convergence. So we say, if we let A be a subset of R, this is something we've been using, okay, been very vital for us. F go from A to R, C be a cluster point of A. Then the function F has a limit L at C, denoted by the limit as x goes to C of f of x equals to L. If for each epsilon greater than 0, there exists a delta bigger than 0, such that for every x element of A with zero being less than absolute value of x minus c being less than delta, then f of x minus L will be less than epsilon. Now, that's what it means to converge. Okay? In this case, we say the limit, we say f of x converges, so I haven't written this down, converges to L at C. If no such L exists, then we say, so this is what I'm emphasizing here, it's new, that f of x diverges. So it doesn't converge, that's that diverges. At C. That's kind of the new definition right here. No such L exists. Okay, so the divergence criteria, here's what it says. Criterion for function limit. Be careful, that's a big word there. It's got two parts. Here's what it says. Again, it's got this set of parts. If you let A be a subset of R, F go from A to R. What else I got? I got C. And C is a cluster point. Okay. So part A is, if L is an element of R, then F does not have limit L at C, if and only if there exists a sequence x of n in A with, so this is a consequence of the sequential criteria for function limits, with x of n being different than c for all n element of natural numbers, and the limit as n goes to c, or n goes to infinity, of x of n equals to c. But what? But the sequence f of x sub n does not converge to L. And then B, the function, we just say generically, does not have limit. Does not have limit. Not have a limit. At C. Similarly, if and only if there exists an x sub n, that's a sequence that's totally innate, with x sub n being different from C for all n element natural numbers. That'll work. And what? The limit as n goes to infinity of x sub n equals to C. But the sequence f of x sub n, just generically, does not converge. So those are two statements. They're very similar. One has to do with a particular L, and one of them just says, well, we don't have any functional limit. And they're related to the sequential criteria for functional limits. And as examples, let's look at some examples. So one out of the book is that the limit as x goes to 0 of 1 over x. This does not exist. The way we can look at it, first of all, graphically. So 1 over x looks like this. Here's this function graph. And as you see, as you get in the neighborhood about 0, there isn't a single y value that the functions get close to. So it's shooting off here to infinity from the right of 0 and going down towards minus infinity to the left of 0. The way that we can show this is that we can consider the following. Consider, so I'm saying it does not exist. This limit doesn't exist. So as an example, the reason why, so this is my proof, we let we consider the best sequence in the domain of this function. I think the best sequence. We consider 1 over n, which is a subset of r minus 0, which is equal to a. So look, the domain of this function 1 over x is all real numbers except for 0. And so that's the way I'm going to write this. So it's all real numbers except for 0. We put a minus. That's the way some people write it. And that's what the domain of the function is. And 1 over n is a sequence in here. And none of the terms of this sequence are 0. But the limit as n goes to infinity of 1 over n equals to 0. So I'm looking at this sequence. It has all the right properties for the sequential criteria for functional limits. But f of 1 over n, which just equals to n, what do I mean, f of 1 over n? So f of 1 over n would be 1 over 1 over n, which is just equal to n. This right here has a sequence. Is unbounded. Okay? Thus, does not converge. And so since I have produced a sequence that's in the domain of the function, the sequence converges to the cluster point 0, what we're interested in. And none of the terms of the sequence are 0. Yet f of that sequence does not converge. Then that says the limit as x goes to c, that's what I'm writing, of 1 over x does not exist. I'll write down DNE for does not exist. That's one example. Let's look at another example. So as an example, consider, or I'll say note, the limit, we'll start with let f of x be equal to the sequence that's, not the sequence, the function that's 1 if x is greater than or equal to 0, and it is minus 1 if x is less than 0. Here's graphically what it looks like. Okay, so that's what the function looks like. What I'm going to claim is that the limit as x goes to 0 of f of x does not exist. Okay, how come that doesn't exist? Well, look, when I put a region about 0, 0 is a cluster point, it's in the domain of the function here, and it's a cluster point. Anytime I put a little region about 0, it's going to have part of it, the function values be at 1 from that region, and part of the function values, output values, will be at minus 1. So they can't be all close to one thing because they're bouncing between 1 and minus 1, depending upon what side of 0, right, or the left. So here, what I'll do is I'll produce a particular sequence. So note the sequence minus 1 to the n over n, that's a equal sequence. That's in the domain of f, which is all bar, and minus 1 to the n over n is always different than 0 for all n number. And the limit as n goes to infinity of minus 1 to the n over n equals to 0. However, the limit as n goes to infinity of f of minus 1 to the n over n does not exist as, let's just look at those terms. So here, if I look at f of minus 1 raised to n over n, as n goes from 1 to infinity. Look, when n is equal to 1, we get minus 1. Okay, so minus 1, I'm over here. The output value is minus 1. When I let n be equal to 2, we get 1/2 for this minus 1 to the n over n. That's 1/2. The f of 1/2 is 1. And then when n is equal to 3, we get a minus 1/3, but that output value is minus 1. And then we get 1 for 1/4, f of 1/4, and so forth. And this is a very famous sequence. It's minus 1 to the n, and we know it diverges. So that tells us about the divergence criterion that the limit as x goes to c, or 0 in this case, of f of x, this f of x, does not exist. Okay. The next thing we want to do is we're going to turn our attention to algebraic combinations of functions and their limits. Remember, we did this type of thing with sequences of real numbers, and then we took the addition of sequences that converge and said, well, they're going to converge, and we knew what they were going to converge to. Same thing for subtraction, multiplication, and division. We're going to do the same thing for function limits. Exactly the same. And the reason it's exactly the same is because we can relate them to sequences. So here we need to start off with some definitions there. So here we'll let f and g be functions that go from A to R. So they're both functions, their domains are both A, and they yield out row numbers. Then we have some definitions. That is f plus g as a function evaluated x is equal to f of x plus g of x. 2, f minus g acting on x is equal to f of x minus g of x. 3, f times g acting on x is the same thing as f of x times g of x. And fourthly, for all x and a with g of x being different from 0, here we'll do it different. We'll say, suppose g of x is different from 0 for all x element of a, then the function f over g acting on x is equal to f of x over g of x. The domain of each one of these functions is A. So, where the domain of f plus g, f minus g, f times g, and f divided by g is A. And the last one's A, provided that g of x is always different from 0. If g of x happened to be 0 in some of those values in A, we just throw those out. We're going to go about 12 more minutes. Okay, here's the big theorem that I was referring to just a second ago. So we're going to let f and g be functions from A to R, and C be a cluster point. Okay. We're also going to let the limit as x goes to C of f of x equal to L, and the limit as x goes to C of g of x equals to M. Okay. Then, oh yeah, exactly what you think is going to happen is what's going to happen. That is, the limit as x goes to C of f plus g acting on x, well, that's going to be equal to L plus M. I'm going to write that a little slower. That's equal to the limit as x goes to C of f of x plus the limit as x goes to C of g of x, which equals to L plus M. Okay. 2. I'm not going to write this out in so much detail, but the limit as x goes to C of f minus g acting on x is L minus M. Go ahead. 3. Limit as x goes to C of f times g acting on x is L times M. And finally, if g of x is different from 0 for all x, element of A, then the limit, man, somebody doesn't know how to erase very well. As x goes to c of f over g acting on x is equal to L over m. If provided, one more thing here, I forgot. There's one more thing to provide. Provided m has to be different from 0. If m is different than 0, hey, we can't say anything. Or if m is equal to 0, I should say. Not saying. Okay, we want to prove this. And you can use, I believe, the epsilon delta definition to prove this, but that's not what we're going to do. We're not going to do that. I mean, it's a limit to functions, but we're not going to use epsilon delta. We're going to use the sequential criterion for function limits. Well, first, we may not prove them all here. They're very similar. But the way we're going to prove it is we need to set up. So we'll let F and G go from A to R. C be a cluster point. Of A and the limit as x goes to C of f of x equal to L and the limit as x goes to C of g of x equals to L. L. It doesn't equal L. What the hell? It equals to M. Okay. Now, for one, we want to prove the limit as x goes to C of F plus G acting on x equals to L plus M. Oh, we can do that. We can show that the limit of an addition is equal to the addition of the limits. That's what we would say that. In the following way, using the sequential criteria for function limits. Here's what I'll say. I'll say let. So how am I going to use the sequential criteria for function limits to prove this? Well, what we're going to do is, this is true by the sequential criteria for function limits. If for any sequence you take in it, then none of its terms are C, but the sequence converges to C. Then F plus G acting on that sequence has to converge to L plus M. That's what we want to show. So we let X of N be a subset of A with X of N be different than C and the limit as N goes to infinity of X of N equals to C. Since the limit as x goes to C of f of x equals to L, then I'm tired of writing sequential criteria for function limits. So I'm going to call it the SCFL. Oh yeah, sounds like a football league. The SCFL is the sequential criteria for function limits. If we just worry about f of x itself, we know it converges to L, and we got this sequence that satisfies the conditions of the sequential criteria for function limits. Then, f of x of n converges, so the limit as n goes to infinity, of f of x equals to L. Similarly, can I say the same thing about G? Yes. Since the limit as x goes to C of G of x equals to M, the limit as n goes to infinity of g of x of n equals to m. Now remember, what I want to do is I want to show that the limit as n goes to infinity of f plus g acting on x of n equals to L plus M. That's my goal. If I can do that, then by the sequential criteria for function limits, the limit as x goes to c of f plus g acting on x is equal to L plus M. Okay, well, what is this? Well, first of all, by definition, what we wrote on that other side of the board a few minutes ago, defining f plus g, is equal to limit as n goes to infinity. Look, that is nothing. I'm just writing that down. Here's where I'm doing work. This is the same thing. F of x of n plus g of x of n. Why? It's by the definition of f plus g. Okay? Now, what do I know about the limit as n goes to infinity of f of x of n? Well, it's equal to L. What do I know about the limit as n goes to infinity of g of x of n? It's equal to M. Meaning these two limits exist. These are sequences of functions, and their limits exist. If you take the addition of two convergent sequences of functions, we proved in a previous chapter that that converges, and it converges to the sum of each one of these limits. So this is equal to, if you will, our algebraic properties of sequences. And that's L plus M. And thus, by the sequential criterion, oh man, why am I writing that out? For function limits, that the limit as x goes to c of f plus g acting on x equals to L plus M. And that's the proof of part one. Not the proof of the whole thing, it's the proof of part one. I think I got a chance. Oh yeah, I got plenty of time. I don't know what you guys do, but the only thing I got to do next is meet with Megan Smith in just a few minutes. Well, Megan, you can wait just a minute. I know all of you are happy that I'm going to make Megan wait. Let's do part two. And then we'll do 3 and 4 together on Wednesday. So 2, we want to show the limit as x goes to c of f minus g acting on x equals to L minus M. I should have included this in the prefacing part for each of these 4 parts. Since, because it's exactly the same, no. We're going to let, in order to use the sequential criteria for function limits, we're going to let x of n be a subset of A with x of n being different from C for all n element natural numbers, and the limit as n goes to infinity of x of n equals to C. Since the limit as x goes to c of f of x equals to L, and, I'll do it at the same time, the limit as x goes to c of g of x equals to M, then we have, then by the sequential criterion for function limits, we have, well, that limit looks terrible. We have, what do we have? We have the limit as n goes to infinity of f of x of n equals to M, and the limit as n goes to infinity of g of x of n equals to L. Thus, the limit as n goes to infinity of f minus g acting on x of n is equal, again, by the definition of f minus g, it's f of x of n minus g of x of n, which equals to the limit as n goes to infinity. This is by algebraic properties of convergent sequences. It's f of x of n minus, come on, minus the limit, that's a minus, the limit as n goes to infinity of g of x of n. Come on, g of x of n. And of course, that's equal to that's equal to L minus M. So by the sequential criteria for function limits, what am I talking about here? I'm finding that if you give me any sequence in the domain of f minus g, okay, that converges to C, but none of the terms are C, and then you find out that f minus g of that sequence converges to L minus M, that means that the limit as x goes to C of f minus g acting on x has to be equal to L minus M. And that proves that part. Okay, I think that's enough for today, and I want to thank you very much for being very supportive of my wife and myself. She's okay, everything's all right, but I'm very sorry we had this interruption in our class, and I hope making up for a class period with this videotape is okay with you guys. Thank you very much for all your support.